What's going on? My name is Tosh Dalday. This is SDG Labs. Welcome to class Physics! Alright, here's the idea behind it, okay? We have this concept of a force. Alright? Now, it's very simple. Force is equal to mass times acceleration. I guess it's this idea that, like, if you have a really big, I'll be honest with you, for the next, like, 2 chapters, that's the only equation we're really going to learn. You know how, like, in the first, like, 4 chapters of physics, all we did was learn 4 equations?
Yeah.
Well, for the next 2 chapters, we're going to do 1 equation. In fact, what is it that you want to do? Do you want to be an engineer or something?
I'm considering engineering fields, probably biomedical.
All right. I took a engineering course over the summer, 381, and I kind of took it just for fun. It was supposed to be this really hard course, and it wasn't easy. I mean, I got a B+, but I was also working full-time, and I've never taken an engineering course in my life. But essentially, all we did was this. We just did F equals ma. That's all we did. The entire class was all about F equals ma. In fact, not even that. We did this. That whole class was all about that. F equals 0. Obviously, it would be a little bit harder than that. We use this thing called a summation sign. Your dad's a calculus teacher, so he would probably call that sigma. But it just means add up everything that you have. So essentially all we're going to learn is if you add up all the forces, that's going to equal to the mass times acceleration. If you look at this equation and I have a box or something like that, and I'm pushing this box with some big force and you're pushing this box with some little force or whatever, if we add up all of our forces, well, first of all, who's going to win?
The bigger force.
Right. I hate to say it, but I mean, I've got a lot of bigger force than you can probably push. Although you're a pretty fit girl, so maybe you're going to compete with that, or whatever. If you add up all the forces in the end, that's going to equal to the mass times acceleration. So there's going to be this overall net force, which is basically my force minus your force is going to be this force. This is what's left over. That's what the left-hand side is, to add up all the forces. The mass times acceleration, I guess one way I like to think about this is, if I have a force, here's what I'm saying is, if I'm pushing with a really big force and you're pushing with a small force this way, then that's equivalent to having somebody pushing with a small force just that way. We can replace my big force this way and your big small force that way with somebody pushing with a medium-sized force that way. Does that make sense?
Mm-hmm.
That's the adding, that's the sum of the forces part. Now the m times a, let's take a look at just that person now. If the mass were really big, and you look at this equation, F equals ma. If the mass were really big, what would F become? If m were really big, what would F become? Something big times A is going to be something big or small?
Big.
It's going to be big. Yeah, well, that kind of makes sense, right? If I'm pushing a car versus pushing a child, or maybe let's make it if I'm pushing a school bus versus pushing some 4-year-old, the force that I would have to push would be huge. It would be way bigger. Does that make sense?
Yeah, that makes sense.
This equation is also saying that it's related to your A. Okay. If I want to make the acceleration to be big, I would need to push with a big force. Or actually, I honestly like to look at it like this. A is equal to F over m. I just divided m by both sides. And it's saying if my m got really, really big, what would happen to A?
it would get big.
No. If F stayed the same, but M got really, really big.
I think you said F got big.
No,
It
M.
would get
M.
bigger as M gets bigger.
As M gets bigger, what? What would happen to
A
A?
gets
It gets small, right? Because if you're taking a number and you're dividing it by a bigger and bigger and bigger number, your answer is going to get smaller and smaller and smaller. And that makes sense too, because if I had a force and I pushed a 4-year-old, and I used that same force and I pushed a really massive object like a bus, the acceleration that I would generate would be really small proportionally. So essentially, what I need to do is justify this equation to you. Are we cool?
Mm-hmm.
Now, I'll be honest with you, alright, there's going to be a few things, there's going to be one other equation that I throw in there, and that's when we deal with friction. That's actually, to be honest with you, technically it's not even a different equation. But the only other curveball that I'm going to throw at you is I'm not going to straight up tell you what the acceleration is. What I'll do, probably, is tell you what the velocity initial is and the delta x is, or maybe the velocity final is, and then the time that it took, or something like that. How then would you think you would get the acceleration?
Just by using some sort of formula.
By using the old school kinematics formula. That's the only trick that I'm really thinking of, the curveball I'm going to throw at you, is that you'll have to calculate A before you actually plug it into this simple equation, F equals ma. We cool? Shoots, bro. Up out.